Hello, my name is Hayden McTavish, and I will be presenting our paper on decision tree optimization. Our work's key contribution is in improving the runtime of decision tree optimization, which we do while retaining accuracy comparable to black box tree ensembles. Before I tell you how we optimize our trees, though, let me start by giving some context for why we're interested in optimizing decision trees in the first place. So we're interested in decision trees because they're a family of interpretable models. The model we show here provides a really clear map from data to predictions, even for someone who might not have a machine learning background. It's just a flowchart leading from true-false questions about the data to predictions. It's useful to have an interpretable model because it lets you incorporate input from a diverse set of domain experts who might not have machine learning expertise but might know a lot about the specific domain you're trying to use machine learning for. It can be helpful for troubleshooting models too, and for making sure that a model that's going to be used for high-stakes decisions is really vetted properly before it's put in a failure-sensitive setting. To be truly useful, though, we can't just have interpretable models, we need to have accurate models. If we want accurate models, decision trees definitely do incur some skepticism because historically they've had really limited effectiveness. Greedy algorithms like CART and C4.5 often grow trees that aren't necessarily useful for a specific problem. They split at the root based on a greedy heuristic, and if they get that greedy heuristic wrong, they're not going to have a very strong tree. But something to think about is whether this is really a problem with the class of decision tree models, or if it's just a problem with the optimization algorithm. To give you some intuition about why decision trees as a model class might actually still be very powerful if we could find the right ones, let me compare them to decision tree ensembles. So ensembles like random forests or gradient boosted decision trees that are considered to be very powerful for a wide range of data sets. So it turns out that for any ensemble of decision trees, there is in fact a corresponding single decision tree which makes identical predictions for any input. So if you look at the ensemble of trees on the left, just a random forest taking the majority vote, you can actually create a single tree by looking at each of these stumps and starting with the first one, putting it at the root, grabbing the second and putting it on each side, and grabbing the third and putting it in the remaining spaces. And this actually divides the search space in exactly the right way that, or pardon, I should say it divides the feature space in exactly the right way that any possible observation is classified in exactly the same way as it would have been for the ensemble. So this little tangent is just to illustrate that the best possible decision tree is, by definition, as good or better than any given tree ensemble. If we search through the space of all possible decision trees, we're also searching through the space of all good tree ensembles. So if you're using random forest or gradient boosted decision trees, you also have the option to use a singular decision tree if you could just find a good enough tree. There's lots of work on finding a good enough tree, specifically for optimizing some objective over all possible decision trees. This usually looks like some optimization function where there's a constraint incorporating sparsity and a misclassification error with a training loss. The most empirically fast of these approaches is branch and bound with dynamic programming, which is particularly promising, although it's worth noting that even fast in this context is still fast at solving an NP-hard problem, so there's still a lot of room to be improving the runtime of these algorithms, and that's sort of the main focus of our approach. So to start, let me give you some context of how branch and bound algorithms work. We start with a full data set, which we predict to be all the data points in the majority class, but then we consider possible splits of that. So any possible threshold we could use to divide this into a tree that has two different leaves. I'm just showing some of them. I don't have a slide wide enough to show every possible feature split. But we split into subsets using those different features, and then we keep splitting as necessary until we're really searching through the space of all possible trees. And then we're able to optimize from there. This probably has you a little concerned because this is a combinatorial amount of possible splits, but there's a number of computational tricks we have to save time. When we have a pure leaf, we don't need to split anymore. There's nothing we could gain by doing so. And when we have two identical sets of points, the optimal subtree for one of those sets, you can just reuse for the other one because it's the same optimal solution. There's also some work we can do with bounds. So I don't have time to get into detail of this. I'm going to have to defer you to the paper, but there are analytical bounds that reduce the search space. Theorems show that you can decide that some partial trees, even no matter how you split them, will never be extended to form an optimal tree. So this really scary search space ends up looking something a little bit more like this when we apply the bounds. The challenge with branch and bound is twofold. One of the problems that we see causing the most issues with decision trees is handling continuous features. There's just so many possible splits you could consider when you're looking at binary decisions that you could make off of that, that this possible search space of all trees becomes really, really wide. There's also an issue with the convergence of bounds. So we do have some bounds that are really useful, but sometimes they don't really kick in until we've searched the space nearly exhaustively. So if they're working well, we might find the optimal tree early and then no longer really need to search much of the rest of the space. But what we find in practice is that often the algorithms will find an optimal tree and then it will still be a while before they're able to prove that it's optimal because they have to go and search all of these different areas of the tree or all of these different areas of the search space of all possible trees. And that means, and they aren't able to prune the branches of that search space quickly enough. Our work is built to help with both of these constraints that branch and bound runs into. So let's talk about our work. Our work is scalability improvements for any branch and bound algorithm. The key idea is to use a black box reference model to inform the search. So we pick some black box reference model where we want to beat or match its performance. Usually for this particular paper, we focused on tree ensembles, specifically gradient boosted decision trees. And we use those ensembles to constrain the search space, but we ensure that black box comparable solutions remain. So to give a quick illustration, there's the space of all possible decision trees that we could optimize over. But instead, we optimize over this smaller circle. And we can be confident that we'll still find some strong solutions in this space because when we choose the smaller circle, we actually prove that there exist trees that are comparable to our reference ensemble within that space. So when we constrain the search space, we always know that we could still find this tree that's comparable to the reference ensemble or another one that's just as good or better. The techniques we use are threshold guessing for continuous variables, lower bound guessing for convergence, and we also talk a little bit about existing approaches like depth and how they relate to this guessing framework of constraining a search space and thinking about what you find when you optimize only within a subset of the space. So threshold guessing is focused on this idea that many thresholds exist for continuous features. If you think about a variable like blood pressure, you may have a data set where the different observations take all kinds of different values for this variable. And if you're considering every possible split, you might have to look at blood pressure 102, blood pressure 103, all the way up through a really high number. And that's going to be a really huge problem because we scale combinatorially in the number of splits we have to consider. We don't just have to consider splits here, but we have to keep splitting each of these individual trees further, considering more splits on blood pressure. And so our goal is to only consider the most important thresholds here instead of looking through all of them. And the way we do that in a principled way is to do ensemble-guided threshold selection. So we fit a gradient-boosted decision tree, and we only look at the thresholds that it uses. We just extract those features. We do some backward elimination to reduce the set a little further, and then we optimize using only these feature splits. So we only allow the optimal tree to search through the space of trees that make these splits in particular. When we do this, we still have theoretical guarantees, as are covered in our paper, that using the same splits as the reference ensemble gives reasonable trees remaining in the search space, particularly ones that are comparable to that ensemble. The second technique is lower bound guessing, which follows a very similar approach to the first technique. So the first guess was features that the reference ensemble uses are probably pretty similar to features that a strong tree would need to use. And the second guess is this idea that maybe the points that a reference ensemble misclassifies are similar to the points that a strong tree would misclassify. So to make that a little more concrete, if we have a subproblem P, just any subproblem we encounter, we can look at the errors that a reference black box model made and see how many of them are in the subproblem, and use that as a guessed lower bound on the number of errors we will make with the best possible tree. So the idea is to apply this to every subproblem recursively, and it gives us a quick estimation of lower bounds that can help with those convergence problems from earlier. So why would you be interested in guessing a lower bound? Well, let's look at some examples. So for a given subproblem, it's always pretty easy to get an upper bound in terms of we know that we'll make at most as many errors as any given tree that is a possible solution. So as soon as we've looked at one single solution for this subproblem, well, we know that we can't make any more errors than that with the optimal solution. We also now have this guess with our lower bound of 3 errors. And so the idea is we use this upper bound to say that anytime we're looking at a tree for this subproblem, if it makes more than 4 errors, we can just toss it out. We don't have to worry about it anymore. And if we're looking at trees that make less than or equal to 3 errors, we actually can just use that tree immediately as a solution to the subproblem. Because, as we'll get into with the theoretical guarantees later, we know that now we have a black box comparable solution to the subproblem. So this can save us a lot of time because we don't have to exhaustively search through every split. We can just find one that matches the black box performance. So the theoretical guarantees that we have are very similar to the ones that we outlined at the start with that set notation. So there is some sparse tree that's identical to the reference ensemble we're using if we are using an ensemble as our black box here. And when we use lower bound guessing, we guarantee that we're still optimizing over a search space that includes that little green point. And so we're guaranteed to be as good or better than an ensemble comparable solution. What's really interesting here is that because both lower bound guessing and threshold guessing have this guarantee, when we use them together, that green point is still in our search space. And so we're still optimizing over a space that is guaranteed to be as good or better than the reference ensemble. So let's talk a little bit, just briefly, about depth as a guess as well. So depth is a pretty standard constraint in a lot of approaches, but one way to think about it in our guessing framework is just to say, if our optimal tree has a depth below some value d, so say we don't need to go as deep as this bottom row, if we remove it, then we're saving a lot of time without reducing optimality. This isn't always the case, but we provide some experimental validation that it's usually a good guess. We also provide some theorems bounding how high to set your depth if you want to make sure that you have a VC dimension that is comparable to the reference ensemble that you're trying to look at and match. Let's talk a little bit about the experiments we have. So we implemented our guessing approaches, all of them, on 2 open source branch and bound and dynamic programming approaches, DL 8.5 and Ghost. And the first thing we have to demonstrate is just this performance change in accuracy and time. So we have time on the log scale and time on the x-axis in the log scale and training accuracy on the y-axis. And we're just going to compare these approaches, Ghost and DL 8.5, with no guessing to our approaches with guessing once we've added those in. And you can see we go from around 15 seconds for our runtime to less than a single second. So huge gains in runtime, and our training accuracy hasn't changed at all, really. It's just the same. So we definitely are able to, we show a number more results in the paper. We're able to improve the runtime dramatically without costs to accuracy with these guessing approaches. We also want to show that we retain the interpretability of our models. So we're showing a number of leaves on the x-axis here versus the training accuracy. And the idea is we want to demonstrate that our model is closer to the top left, which is the really good space, the sparse and accurate models, so really interpretable, really accurate. We're closer to that little space than any of our competitors. So we define this nice frontier set of our star solutions being our solutions with guessing relative to our competitors to show that we navigate this trade-off a lot better. To be a little bit more concrete, our competitors here are CART and BA trees, which are born-again trees that replicate, the idea is to replicate exactly some ensemble that is your target, rather than what we do, which is keeping the ensemble in the search space, but still optimizing a little more beyond that in terms of a trade-off between accuracy and sparsity. So because we do a little bit more optimization, we end up a little bit better along this curve than the born-again trees, and we end up better than CART. We also want to just briefly mention this idea of intuitive decision boundaries. So if you look at Ghost and DL 8.5 before we are looking at our adjustments with guessing, they tend to just time out on even this simple synthetic data set we made that's just like a simple spiral pattern. And when you look at CART and born-again trees, they do all right, but they don't really seem to be capturing this spiral structure in the data set. Meanwhile, when we use guessing, we find that we have these rather elegant solutions that pretty closely match the true underlying distribution of these points. So not only are our models saving us time without losing training accuracy, they also seem to be corresponding to these fundamental trends in data, at least for a few synthetic examples. So to summarize, we provide work that lets us use single trees as accurate as black box models and also interpretable. They are orders of magnitude computationally faster than other optimal approaches, and they're applicable to several existing optimal decision tree algorithms. You can provide this modification to anything that uses branch and bound with dynamic programming. Thank you so much for listening to this talk. Please do stop by our poster session if you have any questions.